Hello, I welcome you all to today's session where we are going to discuss the remaining part of the action of enzymes, and let us understand the formation of enzyme substrate complex in more details and the theories which are popular in explaining this concept. We know that the enzyme binds to its substrate by forming an enzyme substrate complex. So let us take the equation like this. This is substrate A, this is substrate B. In presence of the enzyme, they form a transient enzyme substrate complex which breaks readily to make the enzyme free, plus that brings about the formation of the products. The point where the substrate is bound onto the active site, that is known as the active binding site or active binding site for the substrate, that we have already discussed in the previous sessions. And there are two famous models which explain the formation of the enzyme substrate complex. The traditional model is otherwise known as the lock and key model. So this model was proposed by Emil Fischer in the year 1894, and as the name indicates, as a particular lock can be opened by its own specific key, similarly a substrate of which is having a specific shape to it can fit into the specific active site on the enzyme surface. So here we can compare the lock with the enzyme and the keyhole with the active site and the substrate with the key. This suggests that both the enzyme and the substrate molecules, they have specific geometrical space shapes which is essential to form an enzyme substrate complex. This model also tells that the enzyme action is specific. So if I try to draw this, then suppose this is the enzyme and this particular area is its active site, and this is the substrate which can fit into it. So this is my substrate, this is my enzyme, and this is my active site. So once the enzyme substrate complex is formed, this formation brings about conformational change and the enzyme product complex is formed in the next step. So suppose the substrate breaks from this point. So this globular part is now separated and the triangular part is now separated. So this is now fitting into this. So finally we get the product free as well as the remaining part of the substrate free. So in the first case, I can write that this one is the transient enzyme substrate complex. This one is the transient enzyme product complex. This is the free enzyme, and these are the products. So this is what the lock and key model explains. The second theory, which is otherwise called as the induced fit model, that is an improvisation upon this lock and key model. Lock and key model is easy to understand. Its main advantage is that it is easier to understand and it explains the formation of the product in a more simplified way. But its major drawback is that the active sites of the enzymes are not supposed to be fixed and rigid places as this theory assumes. Like the keyhole, it has a fixed orientation to it, but active sites actual in biological systems are not so rigid, they are dynamic. So in order to make it understand, there was another scientist whose name was Koshland, and he in the year 1959 had proposed that the active site of an enzymes, they are not rigid structures. So when the substrate binds to an enzyme, it may induce conformational change in the enzyme molecule in such a way that it is fit for the substrate enzyme action. So let us take the example of one particular enzyme. So suppose on this enzyme, the active site is present in this shape and the other active site is present in this shape. So this is the active site conformation and this is the enzyme. Okay. Now the substrate which will bind into it, that is having this shape as well as this shape. So particularly these shapes will not be able to bind into this particular sites. So in the next step, the fast part of the substrate has to bind to the enzyme in a specific way so that it brings the conformational change in the second part. So suppose the first part of the substrate is now binding to this particular area. So once this substrate binds to it, this part will undergo conformational change so that this particular part of the substrate can be accommodated to it. So during the third step, you will find that now both the active sites, they have taken a more or less fixed shape. So now the substrate having this part can exactly fit into this and this part can also fit into this. And now this is the enzyme substrate complex. This is the enzyme product complex. Now the enzyme will be made free and I will get formation of this product as well as formation of this product. So these are my products. So this is all about the induced fit model. Actual or active site was like this. Once this fast part of the substrate binds into the active site, it brings about a conformational change in the second active site so that now the substrate can exactly fit onto the active site of the enzyme and it can bring about the formation of the enzyme substrate complex to enzyme product complex. Induced fit brings chemical groups of the active sites into positions that we can say now, and this enhances their ability to catalyze the chemical reaction. According to this theory, the active site of the enzyme contains two groups. One is called as the buttressing group and the other one is called as the catalytic group. The buttressing group is actually the active site of the enzyme where uh, it is not meant for binding to the substrate, but it supports the substrate. The catalytic group is able to make the bonds of the reactants weak either by electrophilic or nucleophilic attacks. The two groups are normally present at a distance. So actually it is the catalytic site which will bring about changes of the bonds in the substrate to form the product, but the buttressing group will actually help the catalytic group to do it. As soon as the substrate comes in contact with the buttressing group, the active site of the enzyme undergoes conformational changes so as to bring the catalytic group opposite to the substrate bonds to be broken. The catalytic group helps in bringing about the chemical reaction actually, and the substrate is finally converted to the product. The product is unable to attach to the buttressing site due to the change in its structure and bonds. Buttressing group, after this reaction is over, it will change to its normal position or normal shape. The product will be released. So the enzyme here that I have written, that you can say as peroxidase enzyme, and its specific substrate is hydrogen peroxide. So now let us compare the lock and key and the induced fit models. Which explain the formation of the enzyme substrate complex and eventually the enzyme product. According to induced feed theory, the active site has two components, but according to lock and key theory, the active site has only one component, or it is behaving as a single entity. In second point, we can say that we have a separate catalytic group and a buttressing group. So there is a catalytic group and there is a buttressing group, but this assumes that there is only catalytic group, and the catalytic group and buttressing group are not separate. According to induced feed theory, once the substrate comes in contact with the enzyme, the buttressing group undergoes the conformational change. So the buttressing group changes over here. So according to the other theory, because there is no buttressing group, so it assumes that the active site, it is not a dynamic but it is a static structure over the enzyme, and that is the main drawback of lock and key theory. Induced feed theory also considers the development of transition state before the reactants could undergo the change. That is another important point, that the transition state or enzyme substrate complex is formed, and then the electrophilic or nucleophilic attack takes place, and then the changes happen. But it develops earlier. But according to lock and key theory, development of transition state is not considered. It only assumes that enzyme substrate complex is immediately formed and it changes into enzyme product complex. No transient state is visualized over here. According to induced feed theory, the catalytic group is believed to be weak by the substrate bonds, either by nucleophilic or electrophilic attack. So here nucleophilic or electrophilic attacks, they do take place, but here no such concept is there. Lastly, the induced feed theory is a non-action over competitive inhibitor. It doesn't, you can say, cover that how competitive inhibitors are, you can say, able to compete with the substrate for the same active site. Once we come for the competitive inhibition, you will understand it better. So this will explain the competitive inhibition, but this will not explain it because it assumes that there is no such active site transition. So having said this, now let us move over to our next part of the discussion, where we will be studying that how mathematically the relationship between the initial reaction velocity and the substrate concentration can be carried out. So before that, let us understand what are the factors that affect the rate of enzyme action, or simply said, what are the factors that affect the enzyme activity. The first one obviously will be temperature. You know that enzymes are specific proteins. Most of the, apart from one or two enzymes which are ribozyme molecules or RNA derivatives, the rest are proteins. So if you increase the temperature beyond a point, the proteins get denatured, and if you decrease it beyond a certain point, then they get deactivated. So obviously an enzyme is active within a narrow range of temperature. The temperature at which the enzyme will show its maximum activity, that is called as the optimum temperature. So if I try to plot it within a graph, and on x-axis I want to show the temperature change, and here I will see the velocity of the reaction. So as temperature will increase, the rate of formation of product will also increase, but up to a point, up to this optimum range. Once the optimum range is reached over here, if you go on increasing the temperature further, then the rate of the enzymatic reaction is actually supposed to decrease. The optimum temperature for most of the enzymes, this range is around 25 to 35 degrees Celsius. The temperature above and below this range, as already I have told, that it affects the enzyme activity negatively. Higher the temperature, that is if it reaches beyond 50 degrees Celsius, then it destroys enzymes by causing their denaturation, and at very low temperatures you will find that the enzymes, they will be having a negative effect on it, because it will preserve the inactive site. Now, having said this, let us move over to the next factor, that is pH. Every enzyme acts as their own optimum pH. If you increase or decrease the pH, the enzyme activity will be affected, and it depends by changing the degree of ionization of the side chains of the enzyme. But most of the intracellular enzymes, they function very well near the neutral pH, that is pH of 7. But only your digestive enzymes, remember the internal environment of stomach is acidic, that means you can say enzymes which are present in your gastric juice, they will be having their optimum temperature range below 7, that is in the acidic range. But once you go to the duodenum, which is at alkaline pH, there the enzymes which are present either in pancreatic juice or bile juice or by secretions of the duodenum itself, their optimum range of temperature will be in the basic or alkaline range, that is above 7. So let us come to the next factor that affects the rate of the enzyme reaction, is the concentration of the enzyme. How much enzyme is present in the system. The rate of the enzymatic reaction also increases with the increase in enzyme concentration up to a point that is called as the saturation point. Once the saturation point is reached, if you increase the substrate concentration, then the rate of the enzymatic reaction is not going to increase or decrease. So here if I plot a graph, then on x-axis, let me say that it is the enzyme concentration, and on the y-axis obviously it will be velocity. Suppose I have 20 enzymes. So now the 20 enzymes are attaching to their substrate and the rate of reaction is increasing. In the system, suppose I am having 60 enzymes. So once it reaches up to the point of 60, then also more and more substrates are attaching to the enzyme and the rate of the reaction is increasing. Suppose now all the 60 enzymes are attached to their respective substrates and they are affecting the rate of the reaction. But suppose you are increasing the substrate, now that there are no longer free enzymes. So if there will be no free enzyme, so if you go on increasing the substrate concentration beyond this saturation point, you will find that even if you are increasing the number of substrate molecules, but the rate of the enzymatic reaction is not going to increase, because there are no free enzymes, no free active sites which will increase the rate of the reaction. Now let us consider the next factor, that is otherwise called as the substrate concentration. So substrate concentration also affects the rate of the reaction. It is understood, because the rate of the enzymatic reaction initially will increase if you are increasing the substrate concentration. At the beginning, the velocity of the reaction will be high, but later on, again, like all the substrates will be utilized and there will be no free enzymes. So if you go on increasing the substrate concentration, the enzyme molecules will get saturated and no active site will be left free. And the next one will be the activators or the poisons of the enzyme. Some chemical substances or molecules can increase the activity of the enzymes, particularly the cofactors that we have discussed, like potassium, magnesium, zinc, molybdenum, etc. On the other hand, if you allow salts of heavy metals, compounds such as cyanides, azides, iodoacetates, they can destroy the tertiary structure of the enzyme, which is a proteinaceous structure. So finally, the rate of the enzymatic reaction is going to be, you can say, negatively affected by this. Having said this, let us move over to the next important part of the enzyme action, and that is enzyme kinetics. And more popularly, we are going to study how the rate of the enzymatic actions are getting affected. So have you ever tried to thought that how the enzyme binds to a substrate and converts them into their products? During the enzymatic reaction, the enzyme binds to the substrate and forms the enzyme substrate complex, which is present in the transition state, which finally breaks into enzyme and the product. And this product is finally released from the catalytic site of the enzyme. This already we have discussed. The number of substrate molecules converted into product per active site per enzyme per second is otherwise called as its K catalytic value or K cat value. K cat value is nothing but it is the number of substrate molecules that are converted to the number of products per unit time. During 1 minute or 1 second, how many substrates are converted into the product per active site? It also represents the turnover number for the particular enzyme, and indirectly its value will be second inverse or its unit will be second inverse. Understanding enzyme kinetics is easier when we plot the respective graphs to understand it. Suppose I am writing that enzyme reacts with substrate to form the enzyme substrate complex. This is a reversible reaction which finally gives to enzyme plus the product. So if I plot a graph and on the x-axis I take time and on the y-axis I take the substrate concentration, then obviously as time will increase, the substrate concentration is going to decrease. So it will show a negative value or a downward value. Similarly, if I take another graph and I try to take time on x-axis and the concentration of the product on y-axis, so as time elapses, more and more products are being formed, so it will be an upwardly mobile graph. As time passes on, more and more substrates will be getting converted to their products, and hence the concentration of the substrate will decrease over time as more and more products are formed, and the concentration of the product will increase over time. So having said this, let us take the slope of the graph. So here this one will be the slope of this graph and this one will be the slope of this graph. So rate of the reaction can be represented as rate of change of the substrate concentration over time. So substrate concentration is decreasing, so I will represent a overall minus sign to it, and rate of formation of product, that will be change in formation of product over unit time, but as the amount of product is increasing, so this reaction will be given a plus sign. Then concentration by time can be called as velocity of the reaction, and it will change the concentration of both the substrate and the product with time. So let me draw another graph where I am taking the substrate concentration on the x-axis and the velocity of the reaction on the y-axis. So initially the rate will be very fast, and after reaching the saturation point it will attain a peak value or a gradual steady value or the saturation point value. So at this point the graph starts bending. If I extrapolate it backwards, the area where it touches the y-axis, this will be V max or the maximum velocity. Velocity of reaction, it changes when the substrate concentration changes with increase of substrate concentration. Velocity of the reaction also increases fast linearly. It from here to here it is a linear graph and then it becomes a plateau. So if we plot it backwards, so wherever it is touching the y-axis, this is the Vmax value. So half of the Vmax will be somewhere over here. Now if you extrapolate it to touch the graph on this side, first you see what I have done. where the linear point of the graph ended and the plateau point started, that was my saturation point, that I extrapolated backwards to touch the y-axis to get the Vmax value. Now I have taken half of the Vmax value, and from y-axis I have tried to reach the linear part of the graph. Now where it will touch the x-axis, this value will be the Km value. Km is that substrate concentration where half of the maximum velocity or Vmax is achieved. The ratio K cat by Km, that represents the efficiency of the enzyme, and this ratio is otherwise called as the specificity constant. This is easier to understand because higher the ratio, the enzyme will be considered to be more efficient. When we measure the velocity of the reaction at different substrate concentration, we get a graph that is almost plateau-like. If we observe it carefully, the first part of the graph is linear, that already I have told you, where the rate of reaction increases linearly with substrate concentration. This linear increase is called as, this part is called as first order reaction kinetics. Because here the concentration is decreasing and the rate of the reaction is increasing. The graph shows a plateau region next, as you can see, where there is no increase in the velocity of the reaction if the substrate concentration is increased. This plateau region, this region, it represents the zero order reaction kinetics. Okay. So from here to here, it is the first order. This plateau region, it is the zero order, where there is no increase in the rate of the reaction. Plateau region, obviously, if you go on increasing the substrate concentration, there will be no overall increase in the rate of the reaction. The velocity has already reached the Vmax value. The velocity is now independent of the substrate concentration. The first order reaction kinetics can be explained by the equation y is equal to mx plus c. This we already know from our mathematical knowledge, where y represents the velocity, then x represents the substrate concentration, then m represents obviously the slope of the graph, and c is the y-intercept of the graph, or simply the intercept of the graph. The equation cannot be used for the plateau region because this is the equation which I clearly told that it will represent the first order reaction kinetics. So this equation we cannot use for the plateau region as it is independent of substrate concentration. So this value will not be there. That is why we need another equation which is more famously given in your book as Michaelis Menten equation. So Michaelis Menten equation will be a mathematical derivation which will be explaining both the zero order kinetics as well as the first order kinetics, and it will explain the curve mathematically. The aim of the Michaelis Menten equation is to establish a relationship between V0, Vmax and Km in such a way that both the first order and the zero order kinetics can be explained. So let me go back to the original equation where enzyme plus substrate by a reversible reaction forms the enzyme substrate complex. This is the reversible reaction under equilibrium and it is called as the equilibrium assumption A. So this is my equilibrium assumption A. This is my first assumption. According to the law of mass action, I can write that Kf is equal to K forward, that is equal to enzyme concentration into substrate concentration is equal to K reversible into enzyme substrate concentration. If we take this ratio, then let us see what happens next. So if I am taking the ratio, then concentration of enzyme, concentration of substrate divided by concentration of enzyme, that is equal to Kr by Kf, K reversible by K forward. And this can be written as Kd, where this D represents the dissociation constant. Besides the steady state assumption, there is another assumption. That is why I have written that it is assumption A. And this is called as the pseudo steady state hypothesis. So what this hypothesis says, let us understand. So here you will understand that the concentration of enzyme substrate complex, it remains constant during the enzyme catalyzed reaction. So we can write that concentration of enzyme into concentration of substrate. So this is K forward, this is catalyzed by K reversible, that leads to formation of enzyme substrate complex. This K catalytic value, that forms enzyme plus product. This means that the rate of formation of enzyme substrate complex is equal to rate of breakdown of the enzyme substrate complex. So rate of formation of enzyme substrate complex is equal to rate of enzyme substrate complex breakdown. So within a second, suppose there is formation of 10 enzyme substrate complexes. Now this 10 enzyme substrate complexes will break down to form the 10 enzymes free as well as 10 products. So we can write that rate of formation of ES, that should be equal to Kf into concentration of enzyme and concentration of substrate. So as this is the rate of formation, then this breakdown can be represented as Kr into enzyme substrate complex plus Kcat into enzyme substrate complex, because previously I had told you that rate of formation is equal to rate of breakdown. So I can write that Kf into enzyme into substrate is equal to Kr into enzyme substrate complex plus Kcat into enzyme substrate complex. So on the right hand side, we can take enzyme substrate complex as common because it is written both times. So the equation now will change into, taking the enzyme substrate complex as common, the equation will change into Kf into concentration of enzyme into concentration of substrate, that is Es into Kr plus Kcat. Now we take the ratio. So taking the ratio, now you will get that enzymes concentration into substrate concentration divided by enzyme substrate concentration, that is equal to Kr plus Kcat divided by Kf value. So this one is otherwise called as the Km or Michaelis Menten constant. So I can write that Km is equal to concentration of enzyme into concentration of substrate divided by concentration of the transient state, or the enzyme substrate complex. So velocity of the reaction is obviously the rate of formation of the product per unit time. So velocity of the reaction can be written as rate of formation of the product divided by unit time. Velocity V0 depends on the rate of breakdown of enzyme substrate complex, the rate at which the transient state will break down, that will be the velocity of the reaction. So I can write V0 is equal to dP by dt. So V0 can also be written as K catalytic value into enzyme substrate concentration. In this system, there will be some free enzymes also, and these free enzymes will not be bound to the substrate, and some of them will be bound to the substrate. So the total enzyme of the system, that will be some free enzymes, total enzyme let me represent as E0, that will be having some free enzymes as well as the enzymes which are present as enzyme substrate complex, because it is not possible that for a biological reaction you will be having almost all the 100% enzymes utilized. So when all enzymes are bound to their substances, then we assume that suppose there were 50 enzymes and now they are bound to the substrate. So at that condition, there will be no free enzymes left. So E0 will be only the concentration of the bound enzymes. As all the enzymes active sites are now occupied by the substrate, now obviously the velocity of the reaction will be maximum. So it will be now Vmax. So Vmax will be K cat, I am writing this equation, into enzyme substrate complex. We have also written that E0 total enzyme is equal to free enzymes plus enzymes present as enzyme substrate complex. So now let us rearrange all this to get a meaningful equation. So to get a single equation, I will write that E0 is equal to free enzyme plus enzymes present as enzyme substrate complex. Km, already I have derived that it is concentration of enzyme into concentration of substrate divided by concentration of enzyme substrate complex. So if I make E0 minus Es here, then I will get the total enzyme E. So now E is replaced in the equation of Km. All I am doing so that I get a single value. So now Km becomes E0 minus Es into concentration of S divided by enzyme substrate complex. Simply I have made these two equations go at one step. Now I have to cancel out certain factors. So on both the sides I have to multiply something mathematically so that the values cancel out each other. So on both the sides I will be multiplying the substrate concentration so that I cancel out the values and bring them to the minimum. So once I am doing this, the value or the equation changes into Km is equal to E0 into substrate concentration minus enzyme substrate concentration into substrate concentration divided by Es. So now this Es and Es, they will cancel out. Again I have to rearrange. So now Km will be E0 into substrate concentration minus substrate concentration, because these have cancelled out, and divided by Es. So this can be now replaced as E0 can be replaced as Vmax by K cat value from the previous equations. So now I can write that Km is equal to maximum velocity into substrate concentration minus substrate concentration and divided by K cat value into enzyme substrate concentration. Now this K cat into enzyme substrate concentration, that is equal to V0. This already previously we have written. So now if we substitute, Km will become V max into substrate concentration minus substrate concentration divided by V0. If we take S to this side, so Km plus substrate concentration, that will be V max into substrate concentration, because here this side it was minus, here if we change the side it will become plus, so it will be V0. Then again you rearrange. So rearranging, we get that V0 is equal to V max into substrate concentration divided by Km into substrate concentration. This implies that if the substrate concentration is very large, then the value of Km is very less in comparison to substrate concentration. So in this case, when Km value will be less, then it can be ignored. So now this, ignoring the Km value, now the equation will change into V0 is equal to V max into substrate concentration divided by only substrate concentration, because this value you have neglected. So from this equation we can write that V0 is equal to V max, because substrate concentration is comparatively less. So when V0 will be V max by 2, means the velocity will be exactly half of the maximum velocity, then you can write that V0 is equal to V max into substrate concentration divided by Km into substrate concentration. It is this equation I am writing. So by cancelling out, we divide both the sides by 2. So V max by 2 will be V max into substrate concentration divided by Km plus substrate concentration. So if you cross it out, then half will be substrate concentration into Km into substrate concentration. So again, if you change the sides, multiply this by 1, multiply this by 2. So it will be Km into substrate concentration is equal to 2 times substrate concentration. So Km is equal to 2 minus S, sorry, minus substrate concentration. So Km is equal to S. So this tells you that Michaelis-Menten equation is important from the point of view that the Km or Michaelis-Menten constant is a mathematical derivative which tells you that substrate concentration at which the chemical reaction catalyzed by an enzyme attains half of its maximum velocity. It also indicates the affinity of the enzyme to this substrate. A higher Km value indicates a low affinity, whereas a low Km value indicates a higher affinity. This Km value for most of the reaction, it will lie between 10 to the power 1 to 10 to the power 6 moles. Michaelis-Menten equation obtained after a single algebraic manipulation, obviously we have seen is equal to V is equal to V max into substrate concentration divided by Km into substrate concentration, where V is equal to measured velocity, V max is maximum velocity, S is equal to substrate concentration, and Km is equal to Michaelis-Menten constant. So now let us see that if I represent it graphically, how does it look? So this is my substrate concentration. This is my velocity or rate of the reaction. So we know that reaction with enzyme will give you a first order graph, then a plateau, and reaction without the enzyme will give you a straight line. So this is with enzyme and this line is without enzyme. So maximum rate will be the point where the plateau starts. So this value will be your V max. Half of V max will be somewhere here. You make it extrapolate here and touch it over here. So this is your Km value. So having said this, Michaelis-Menten equation derivation, if you are finding it difficult, then you need not remember it. But the thing is that you should be able to understand how it is mathematically derived. Now let us consider the inhibition of enzyme action. That is the last part of this discussion. Certain chemicals severely inhibit the action of enzymes. The reduction or the stopping of enzyme activity altogether due to the presence of these chemicals is called as enzyme inhibition. So enzyme inhibition we will study in the next part of our discussion. Thank you.